All right. So looking at this electron configuration, how can we determine how many valence electrons there are? It's the highest number, the highest n value in the electron configuration. So because there are 2 of the 4 s's, and again, that 4 is our n value, then that tells us that there's 2 valence electrons. Let's see. Anastasia, do you remember what we call these electrons? Electrons that aren't in the noble gas core but don't have the highest n value. Do you remember what we call those, Anastasia?
Pseudo electrons.
That's right, pseudo-valence electrons. Very good. And they do a little bit of chemistry as well. And to predict the kind of chemistry they do, we really need an orbital diagram. Okay? So, let's see. Brielle, are you there?
Yes.
All right. So, Brielle is going to, well, she can tell us if she doesn't want to here, but what we're going to do here is we have a whiteboard here, Brielle. Can you bring your mouse up here? There we go. So, Brielle, I want you to draw for us a orbital diagram, okay? I'll start you off by drawing. Oh, wait. So we got to go over here to the tools bar. We got to pick the pen. I'll start you off by drawing an arrow. And this is what? What is the label here?
On here it says EPA, but I don't know what that means.
On where it says EPA? Oh, on the slides?
Here on the notes.
Okay. Well, don't look at the notes for this one because we don't want you to just copy.
Okay.
But that's energy. That's right. Energy.
Energy.
Okay. All right. So, Brielle, try to draw us our orbitals, and we'll see if you can label them. It's kind of hard to get good handwriting on the computer like this. Did you go over and choose the pencil already? Oh, you got it. Good job. You got a pencil in there. Was that you that made that little mark?
No, I don't think so.
Oh.
Let me see. I'm going to try and draw this. Oh, there you go.
Okay, good. So there's our first orbital, and it's labeled 1s. Very good. And our next orbital is labeled 2s. Very good. So now, okay, now it looks like she's putting in a what? What is this you're putting in there, Brielle?
2p.
2p. Now, I don't know if you did this on purpose, but you have to make sure that this is higher in energy than the 2s. Does that make sense?
Oh, yeah, okay. Can I, like, erase it?
Yeah, let's see. Do we have an eraser? Where's our eraser? Maybe this is an eraser?
Wait,
you erased it. Good job. How'd you do that?
I just clicked the, like,
undo?
The undo thing, yeah.
Okay, good. All right, so we got 2s, and now we're putting in there 2p. Very good. Now, let's go far enough so that the electron configuration, I'll write the electron configuration up here for argon, okay? Let me see here. But we got, or sorry, for electron configuration for, can I write? Why can't I write? Oh, there's my problem. I'm writing in white. Here we go. So the electron configuration for iron is what I'm going to draw here. All right. It equals.
Memorize this chart.
That's what I'm about to show you here. That yes, we do have to have it memorized, but it's not memorization because what we're going to be what we're hopefully doing is following the elements on the periodic table. Okay. So argon 4s2. 3d 6. Okay, so we got 3p. Now, what are you drawing now? It looks like you're drawing the 3d.
3d, yeah.
Now, how did you decide to draw the 3d next after 3p? Just cause?
Yeah.
Okay, so don't draw anything else. I'm going to show you one thing. Right here, right here, I'm going to sneak in here, in between the 3p and the 3d, I'm going to sneak in a 4s.
Okay.
Okay, ooh, that looks horrible. But, okay, so how did I know the 4s came before the 3d in terms of energy? Right, that's the question. And I think, was it Chance who was asking, are we going to have to memorize this, or whoever it was?
I have no idea how to do this properly.
Yeah, so where are we getting this information in terms of what is higher or lower in energy? Right? Braille, you got your hair blow dryer on?
What?
Something's really loud if you want to put it on mute.
Oh.
So, how are we going to know? How are we going to know? Well, this is the way we're going to know. Okay? Let's go over here to the, let me share my screen again, and let me bring up the picture of the periodic table. Where's the picture of the periodic table? There it is. Okay, so looking at the picture of the periodic table, it's the periodic table that's going to guide us to know exactly how we have to draw this orbital diagram. Okay, so let me find our spot here. Okay, so there's our energy. All right, and now we're going to start off with 1s. Now that part we kind of want to know, but it really, the periodic table tells us, because what we're trying to do is trying to depict where the electrons would reside in any given atom. Okay, we could choose a target like iron here if we wanted to and work our way up to it, but what we want to recognize is that these are the electron configurations for any given atom as the electrons would be filling. And so because we start with hydrogen and helium, that's the first row, that's 1, their n value is 1, right? For n value equals the location or the row on the periodic table, right? Let me bring out a periodic table here that I can write on, right? So n equals 1 here, right? N equals 2, 3, 4, right? So the row corresponds to the n value. And this block, what block is this block, Camilla?
It's the S block.
That's right. That's right. This is the S block. So because I'm starting off with 1, n equals 1, right? The first level here, hydrogen and helium, right? So in my orbital diagram, I start off with 1s. Then the next electrons are going to have electron configurations similar to that of lithium and beryllium. And so I want to draw an orbital that represents these two electrons. That is going to be 2, n equals 2, because we're on the second row, n equals 2, and this is the S block, so 2s is next. All right, that's followed by these electrons over here. So what subshell do I give to these electrons? Any idea, Camille Dinsdale?
Is that the P block?
This is the P block. What n value should I give it?
3? I don't know.
No, I'm still just on the second row, right?
Oh, the second row, and then if you go down one more, it'll be 3.
That's right. So this is going to be 2, and it's the P block, all right? Now, how do I know that I need to write 3 of these? Do you know, Chance, how I know I had to write 3 of these based on our periodic table? Any ideas?
Is it because there are 6 elements?
That's right. Does that make sense, Chance? 6 elements across, and each one of these has a spot for 2 electrons. So that's 6 electrons across. I'm going to need 3. Did that make sense, Chance?
Boron to neon.
We would, if we filled 2p all the way up, it would take us from boron to neon. That's right.
Okay, yeah, that makes sense.
All right. So then, Chance, what would go next after 2p based on the periodic table?
The ES.
3s. That's right, 3s, where that's representing where electrons for sodium and magnesium would go. Very good. All right, so Daisy, what's after 3s?
It'd be 3p.
That's right, 3p, representing what elements, Daisy?
Aluminum through argon.
That's right, and so we have 6 elements, 2 electrons in each of these orbitals, so I need a total of 3 orbitals there. Now, this is where kind of the next, the point where we kind of got stuck on our last one. After we're done with argon, 3p, what is the next in energy? That's going to be potassium and calcium. Who is it? Edgardo. What's the next one here? What's our next subshell going to be? Edgardo, are you there?
I'm not too sure. I'm still figuring everything out.
All right. So, do you have any ideas, Emily Eddington? What's our N value for potassium and calcium? Ephraim? No, Ephraim doesn't have his microphone going. Oh, Ephraim says 4 in the chat. Very good. So 4, potassium and calcium are 4. And Ephraim, do you know the L value? I mean the L value or the letter that corresponds to that L value?
4s.
Okay, thanks, Emily. That's right, 4s. So 4s. So we went from 3p to 4s. We didn't go to 3d first. And how did we know? We knew because we were just following these electrons in the periodic table. Now, here's kind of a more difficult question. Hopefully we remember from last class. But as we go into scandium to zinc, all right, so this is for Fala. Are you there, Fala? How many, or what is our next subshell after we go for fill our 4s?
3d.
3d. Very good. 3d. And do you know, Fala, how many orbitals are going to be in that 3d?
5.
5. That's right. 1, 2, 3, 4, 5. Very good. So what we're seeing basically is that this orbital diagram, which is a little bit too big, so I'm going to draw it a little bit smaller here. 1s, 2s, 2p, 3s, 3p, 4s, 3d. We know this information simply by looking at the periodic table here. Okay?
I have a question.
Yeah, go ahead.
This might be like a really stupid question, but like, what element are we doing this for? Like, what? I'm confused.
Well, we don't need to have an element that we're doing it for, and we didn't really pick one. But if we wanted to pick one to kind of, ease our mind and give us some information about that, let's pick cobalt. Okay? So
can we just draw this without knowing an element? Like, we're just going through?
that's right. Because all of the elements are going to have their electrons somewhere in here, right? If we did something like beryllium, 4 electrons, we'd only fill up, right, the electron configuration for beryllium. If I did beryllium, for example, electron configuration, let me get this out of the way. Electron configuration, 1s2, 2s2, right? So that would be 2 electrons here and 2 electrons there, right? And that would be fine. But let's say we want to go to cobalt. If we want to go to cobalt. Now, if we want to go to cobalt, I shouldn't have drawn these as a staircase. They should be just flat. If we want to go to cobalt, what electron, what's the last electron here? Where does that reside? Let's see, who's next? Eleanor? If we want to go to cobalt, where does our last electron that fills up cobalt going to be in our our orbital diagram here? You there, Eleanor? Let's see. Catherine, how about you? Where is our last electron reside if we're talking about cobalt?
So does that mean which of those
Subshells.
cells isn't filled all the way?
No, it means where's the last electron going? Which of these subshells is our last electron going to be in cobalt?
The second one?
What do you mean the second one?
The second line.
Oh, the second line for 3D?
Yeah.
Okay, very good. So I was just looking for 3D as an answer. That's the
Okay.
the last subshell. But very good. So let's fill this up with cobalt, right? So as we saw, all of these electrons are going to be filled. And then the last 7, 1, 2, 3, 4, 5, 6, 7 are going to go into this 3D. 1, 2, 3, 4, 5, 6. And then that's where we're referring to that second line there being the one that has the last electron.
Is the one next to the 3s a 3p?
Oh, sorry, yeah, that's supposed to be 3p. Good, thank you.
Okay. Thank you.
All right, so then how many unpaired electrons do we have, Kylie? How many unpaired electrons?
3?
3. 3 unpaired electrons. And what did we say about unpaired electrons? What do they relate to, did we say?
Is it the valence electrons?
No. Unpaired
Not
electrons related to a property we said was magnetism, right? Or what we call magnetic susceptibility. So the more the unpaired electrons exist, the more magnetic susceptibility or the more magnetic a material would be. Okay? Now that we're at this point, we can also make a prediction about the kinds of ions that cobalt would like to form. So the electron configuration for cobalt, right? We got an argon core, and then this is the argon core, this little bit right here, right? And then we have argon 4s2, 3d6. Hopefully everybody's comfortable with that now in terms of how to write an electron configuration for an element, right? So let's think about the kind of ion that cobalt would like to form. What kind of ion would cobalt like to form? Let's see. Koa, are you there? Can you type into, are you there? Okay, great. Tell us, what do you think? What kind of ion would it like to form here based on this information?
I think it would form a +2, so to get rid of those electrons that are paired.
So it will form a
In the
+2.
3D.
It will form a +2. That is correct. However, the way it will form a +2 would be to get rid of its valence electrons. And how many valence electrons does cobalt have?
2.
2. Not an equal sign there. Sorry about that. This shouldn't be an equal sign either. Cobalt has 2 valence electrons. And which ones are they, Koa?
They're the ones in the 4s.
That's right, the 4s2. So by forming a +2 charge, all we leave behind is the 3d6. Good. So that's one of the ions that'll form. Very good. Yeah.
Why is it 3d6? Because isn't cobalt like the 7?
Oh, sorry. We missed 1 electron. Very good. Thank you.
Okay.
So we knew that simply by counting 1, 2, 3, 4, 5, 6, 7. Right? Very good. All right. Now we'll let Koa answer this one as well because he already alluded to what the next ion would be. What do you think, Koa? What would the next ion that cobalt would form?
+4.
+4. How did he know that? Let's see. Quincy, are you there? Or maybe you don't have a microphone available. Rebecca, How did he know it was a +4, do you think?
I'm not really sure.
Okay. We're going to try to clean this up a little bit because we got lots of stuff going on. But I'm going to rewrite an orbital diagram here for, I'm going to say argon core. And then outside the argon core, I have my 4s2 and my, sorry, not 2, just 4s and 3d. And we said that, whoops, man, cobalt had an electron configuration of argon, 4s2, 3d7, right? And
Yeah.
we said that it became a cobalt +2 ion because elements like to lose their valence electrons if they can. Okay? And now, the next thing that will occur in terms of ions, it's been told us that we're going to form a cobalt +4 ion, and we're going to talk about how we know that that is the case. And this is how we know. If we take a look at what's left here, right? So initially we had 2 electrons here and 7 across here. But to go to the cobalt +2, we lost these 2 electrons. So now we just have 4, 5, 6, 7 electrons. Right, Rebecca?
Yeah.
All right. So how else can this element, or this species, because now it's an ion, right? How else can this ion find stability? Do you remember that, Rebecca?
By adding 3 more electrons?
Not by adding 3 electrons in this case, but by making a half-filled subshell. A half-filled subshell.
Oh.
So how would it make a half-filled subshell? What would it have to do? In this case,
Add 4?
it would have to lose these 2 ugly electrons that are making it look asymmetric. Does that make sense?
Yeah.
And so we'd be left with what? 3D what here?
3D 5?
That's right. 3D5. Very good. So it would be feasible to predict that cobalt will form a +2 ion or a +4 ion. Does that make
Okay.
sense?
Yes, thank you.
Okay. Excellent. All right. So hopefully you guys are comfortable drawing your own orbital diagrams, right? Drawing your own orbital diagrams because, well, you just follow along the periodic table. Maybe we should have one more example here in which we do something like thallium. Thallium. Okay? We're going to write the electron configuration for thallium first, and then we're going to write, let's see, what else are we going to do? Oh, draw the orbital diagram. Electron configuration and the orbital diagram. So, thallium. Why don't you guys break into groups? We're going to write the electron configuration for thallium and then the orbital diagram. We want to use the noble gas core. Even in our orbital diagram, we're going to want to use the noble gas core. So just say xenon and then draw the rest from there for your orbital diagram. Okay? So we're going to use the noble gas core in both our electron configuration and our orbital diagram to save ourselves some time. But again, we're looking for thallium here. So I'm going to break you guys up into groups, and you're going to work on this amongst each other, or with each other. Let's see if you can. We'll have 6 groups here. There we go. So go ahead and go into those groups and see if you can get the electron configuration and orbital diagram for thallium.
Hi, how are you?
Good. How are you?
Good.
Okay, so
Since we're working on thallium, he said to start with the xenon
as like so we can cut all of the beginning stuff out. And so I just have been working on it. It would be, if I have it right, I think it's first is 6S, and then it goes to 5D, and then 6P.
Yeah. Yeah, do you have to put 6P1? I don't know.
I think you just write 6P, and then like when you have the 3 lines, you just write the one on like across the line. I don't know if that's the right mode.
Gotcha. Okay, so then we also have to draw it out.
Yes. So it's like we have the 2 electrons on each one. That just fills the table. So I just have, because the 6S is just 1 line, and then the 5D is
the 5 lines, and the 6P is the 3 lines.
I think that's what I have.
Okay, so one thing to look at there is, so at 1, 2, 3, 4, 5, 6S, that's where you said outside of xenon, right? Cesium and barium. That's 55 and 56. But then, where do we go from 56?
We start with the D block, don't we?
We first, what does it say down there?
From 57 to 71.
Yeah, 57 to 71. So that needs to go before the D block. Yeah. So what would that be? 57 to 71. Anybody have any ideas? It's F. That's right. What's our N value? What do you think the N value is?
Gosh, I don't know.
All right. So it's on the 6th row. The D value is going to be 5D, like you said, right? But these F values is actually going to be 4F. So it's 2 less on the N value, just like D block was 1 less, it's 2 left.
Okay, so with the F block, it's 4, like the first line is 4, and then the N is 4, and then the next line is 5.
N is, that's right.
Okay.
I can't tell how to make it so we can draw on our whiteboard. I thought we could draw on our whiteboard. Anybody see how they can do that?
Oh, I didn't even know this was the whiteboard.
Oh, somebody can draw on it. Great. I don't know.
Oh, yeah, here I can draw it.
Go ahead and draw us a xenon atom, and then draw us an energy diagram. Why is it you? Oh, I see. Okay, so if I click on here and make myself a presenter, but okay, very good. Hopefully we're not too high there. So above that goes what?
The 6S.
6S, yeah.
Wait, I put it above it?
Because we're talking about an energy diagram.
Right here?
Yeah. Good. So I think we got it. I'm gonna close our chat rooms now, and we'll join the main group. Okay.
Okay.
Oh yeah, I have to go here to do that. All right. Okay. So let's see what we got. Sarah, are you there?
Yes.
Do you want to walk us through what you guys learned in your group in terms of the maybe first our electron configuration, If we're looking for the electron configuration of thallium, right? What do we got?
Yeah.
What do we got?
We
Well, do you want to try to give it a shot?
yeah. So first it would just be xenon,
Uh-huh, that's right, our xenon core.
and then that's 6s2.
Very good. She knew it was the 6 because we're on the 6th row, S block, 2 electrons. Now here's the tricky part. Where'd you go next? Say that again.
Long.
I can't hear you very well. So, you want to try it one more time, talking?
Is that the F block?
That's right. That's right. What do you think is the N value for that F block? We're on the 6th row, so if it was the D block, it would be 5D. But for the intertransition metals, it's actually 4F. 4F.
Can you explain why S2?
6S2.
Yeah.
So, trying to get to thallium here, right? Here's thallium. Can you see my cursor there? Yeah. Okay. So we're trying to get to thallium. We go back to our noble gas, xenon, and then working from 64 going to 65. Or no, does that say? I got too small for me. Here we go. Xenon 54 going to 55 and 56. So this is the 1, 2, 3, 4, 5, 6. 6, n equals 6, 6th row. And this is the S block. So 6s2. Does that make sense?
Yes.
Now, after the 6s, so how do we know this was n equals 6? Because it's on the 6th column. 1, 2, 3, 4, 5, or 6th row. 1, 2, 3, 4, 5, 6. How do we know it was L equals 0 or S? Because this is the S block. All right? So, 6s, 2 electrons. We're working our way over to thallium. 56, now we have to go 57 to 71 basically here, which is our F, our 4F block, 4F subshell.
How did you know it was 4?
How do we know it was 4? Well, we didn't really until I told you, but there was a couple of ways that we could have thought about that. One is, just like the D block is N value is 1 less, the LF block here is its N value is 2 less, and if we think about our possible, if N equals 3, for example, oh no, sorry, not N equals 3, if N equals let's get back our periodic table here. If n equals 1, 2, 3, 4, 5, 6, if n equals 6, right? If n equals 6, fresh piece of paper here. If n equals 6, L can equal what? What can L equal? It can equal, 0 all the way up to 5. And in the case of our F block here, L equals 0 here. L equals 1 for our P block. L equals 2 for our D block. And L equals 3 for our F block. So we're talking about L equals 3. All right, so if L equals 3, M sub L, while we're here, well, we don't have to do this right now, I guess. We can do that in a bit. But the possible n values for L equals 3 are what? What's the possible n values for L equals 3?
4.
Yeah. N could be 4 all the way up to what? Infinity, right? It has to be at least one more than L. So because we knew that the first n could be 4, and this is our first F block, that's one way that we knew that n could be 4. I think that would be a little bit confusing to most of you, though, so I think that the easiest way to remember is that just like the D has n minus 1, the F has n minus 2. So if you're in the 6th row for the F, then this is the n equals 4 for that F block. And this second row here is n equals 5 for that F block. Okay, so let's get this a little bit smaller. Let's go back to our, where is our thallium electron configuration? 4F. Now, how many electrons are going to go across the 4F? Whose turn is it to answer? Yin, Kim Yin. How many F electrons are we going to have across to fill up that F block there? Kim?
15.
All right. 15 is close. Let me show you why it's only 14. Okay? This lanthanum, which is shown, and it's really just because of our particular periodic table. The lanthanum and the actinum here, these have been brought down. They're really in this spot right here, and the F block is cerium to what is this one called? Lutetium. That's what it is. Okay? So, another way that we knew that it was going to be 14, 4F14, is going back to our L equals 3. If L equals 3, the possible M sub L values, who else do we have down here? Anybody? Going back to the top of the list again. Aisha, what are the possible M sub L values if L equals 3?
Would it be positive 3?
That's right. Negative 3, negative 2, negative 1, 0, positive 1, positive 2, and positive 3. That's a total number of 1, 2, 3, 4, 5, 6, 7 possible M sub L values, which corresponds to 7 orbitals or 14 electrons. So that's one way, another way that we knew that this was 4F14. Okay, then, after we're done with 4F14, what's next, Alyssa? What's next after 4F14? That's stopping at element 71 with 4F14. So now we go to hafnium. Or we actually go from lanthanum to mercury. Any ideas, Alyssa? Or is your mic not working again? Oh, Ephraim told us there. Good. That's 5D10. 5D10. All right. So, how do we know it was 5D? This is our 6. 1, 2, 3, 4, 5, 6 here. 6. We're in the D block, and we have 10 electrons to get all the way across the thallium. So, 5D10. I don't know if Ephraim answered for that question or a different one, because that was a long time ago, but same answer. Okay, good job. So, 5... Yeah.
Why is it 5, not 6?
Is it supposed to be 6? Oh, you're right. It's 6D10, not 5D10. It's 6D10.
Okay.
There we go. Because we're not in the 6th here, is it? It's 1, 2, 3, 4, 5, 6.
You're in the 6th, though. I thought it was.
Oh, right. But we only go down 1 less. So it's, wait. 5D. 5D. Yes, it is 5D. Is that what you said? I had 5D to start off with, right? 4, 3, 4, 5. That's right, yeah. So here we go. 1, n equals 1, n equals 2, n equals 3, n equals 4. So for n right here, our value is not 4, but what is it, Alyssa?
Oh, I was just seeing if it worked now.
It's
Can you hear
working,
me now?
yes. Can you tell us the n value for this block right here, where the cursor is?
The n value would
Yeah.
be 5. For that row would be 3, right?
3, that's right. And for this row below it, the D block below it, 4, and the D block below that is 5. Yeah, very good. So this is supposed to be 5D10 there. All right, and then after we got 5D10, what do we get? Let's see, who's next? Anastasia. After we get 5D10, what's the last electron to get us to thallium?
6p.
6p. Very good. And then what's 1? That's right, 6p1. Very good, Anastasia. So Brielle, how many, what do you call them? Valence electrons does this have? How many valence electrons does thallium have?
Is it 1?
Okay.
Or 3 because of this S and P.
That's right. The answer is 3. It's the ones that have the highest n value, so those are our answers there. Okay?
Question.
Yeah,
If they're the same, you just add them up.
that's right. That's right. The ones with the highest n value, you just add up all. So if there's 2 here and 1 there, then it's going to be 3. And that's what we call our valence electrons. Our valence electrons. Now, I'm going to draw the electron configuration for this. All right? So, we need to give ourselves... What's that?
Pseudo-valence electrons for that one.
How many pseudo-valence electrons? 24? 24 pseudo-valence electrons. Stuff that's outside the core, but not valence electrons. All right? So, let's look at thallium, its electron configuration here, and try to find out what kinds of ions it would like to form. I'll have up here thallium, xenon, 6s2, 4f14, 5d10, 6p1. All right, and now we're drawing electron configuration. Xenon, to save our souls some time, 6s, 4f14, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Good. 4f, and then a 5d. 1, 2, 3, 4, 5. 5d, and then 6p. Okay. So we got, oh, did I make a mistake? Oh, no, that's right, that's right. 6s2, 1, 2, 6, or 4f14, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 5d10, 1, 5, 6, 7, 8, 9, 10, 6p1. Very good. So, there it is. That's our electron configuration. And then we can start thinking, what are some possible ions that thallium might want to form? Whose turn is it? I think we were Anastasia. Brielle? Is it your turn, Brielle? What do you think? What kind of ions might we might be forming here?
I actually answered the last question, but I don't understand that. So.
Oh, okay. Sorry. Sorry. Camilla's turn. Ugh. What is a possible ion here? Any ideas, Camilla?
The ions kind of confuse me, but does that have something to do with that we have like 5 electrons not filled or something?
Well, actually, what we would like to do is the 3 ways to kind of find stability is have a noble gas core, if we can end up with just the noble gas core, how many electrons would we have to lose to get a noble gas core here? Yeah, it's like 27, right? You'd have to lose all these to get a noble gas core of xenon. So that's not going to happen.
Mm-hmm.
We can lose, we can empty shells, subshells, or have half-filled subshells. So those are the other two ways. Empty half-filled subshells or empty, or half-filled subshells or empty half-filled subshells. So, if we lose this electron, what will that give us? An empty half, empty subshell, right?
Mm-hmm.
So, it would be feasible to think of a thallium plus 1. That would be losing that electron. And then, what would be next? Who was that? Was that Camilla? So, Camille, what do you think? What would another thallium ion?
So would you be going down to the row below, the 5?
No, we're going to be looking at our highest energy, 6s, right?
Plus 2?
It would be losing these 2 electrons to form a what?
Plus 3?
A plus 3 ion. That's right. So you were thinking just make a half-filled subshell here?
Yes, but
Yeah. No, that's fine. That's fine. That's a fine idea. So, and it's not always completely straightforward with these transition metals, or what we call post-transition metals. So bringing up the periodic table again here. When we're dealing with these transition metals, or in this area, which is our post-transition metal area, it's not always straightforward, the kinds of ions that can form. And, you know, honestly, we haven't found all the compounds that exist with these elements. So we're always constantly looking for different kinds of compounds, and we always learn new information about different charge states. Well, it took a whole class. Yeah, go ahead.
Oh, sorry. So I'm just confused on why you couldn't like halfway fill the 6p and have like a negative 2 charge. So if you added like 2 more lines to like halfway fill the 6p, then you would technically be gaining electrons, which would put you in the negative. Like, would you ever have like a negative charge?
Like a thallium -2 ion? I don't know. I've never heard of a thallium -2, but that, I mean, that's the kind of thing that people would be looking for because of that sort of rationale. They would say, wait, this would fill a half subshell. It might add some stability. And it might, because if you fill that half subshell, you kind of approach this staircase almost, right? You get closer into this range. Now, these semi-metals have kind of interesting properties. They can go both ways, and so they find stability by gaining and by losing electrons, right? On the right side over here, we know that these are predominantly gaining electrons to find stability. These ones all lose electrons to find stability. But I wouldn't be surprised in the future if you were to see something like that. And you could even look it up and see. And usually if thallium is going to form a -2 charge, it's not going to be part of an ionic compound. It's not going to behave like a metal. It's going to behave like a nonmetal and form more of a molecular-like compound. And that's what,
because it's getting closer to the staircase.
yes, it's getting closer to our region here of nonmetals, right? And bonds between nonmetals are covalent in nature. They're sharing electron density. And you get all sorts of interesting things happening when you approach elements in this area and form compounds with them. Good. So what we've provided ourselves with is basically a tool. The electron configuration is useful only if we can really visualize our orbital diagram. If we can take our electron configuration and visualize our orbital diagram, then we can answer questions like, hey, you know, what kinds of situations would thallium find itself in to stabilize itself? And so in the future, when we find, for example, a compound, a molecular compound that contains thallium, nobody's surprised because we say, oh yeah, thallium can fill up that half subshell there and gain some stability, right? So those are the kinds of rationale that we've kind of supplied ourselves by understanding the orbital diagram from the electron configuration. Okay, sorry that took so long, but I think it's valuable. I think it's valuable because it unlocks information about not just these elements, but also about all of these elements, right? In terms of ways that they can find stability. And it's not always cut and dry, so the questions that can be asked are kind of minimal. If I asked how many valence electrons for nickel, I think that's a reasonable question, and I think we need to be able to answer that really quickly, right? We could write out the electron configuration and think about it a little bit deeper, but because of its location on the periodic table and because of our experience, I think we should be able to know that all of these electrons in here, all of these atoms in here, all have the same number of valence electrons. Anybody know that? Anybody want to take a stab at that? Let's see. Aisha, how many valence electrons does nickel have? Or Chance, did you want to take a stab at that?
Is it 2?
That's right. Nickel has 2 valence electrons, and it's these ones, potassium and calcium. And that's, again, we'll see some exceptions, but in general, always willing to form +2 charges. All right, so I think we learned something valuable, even though it took a little bit extra time. I think at the rate we're moving, gentle people, we're probably not going to have anything more than a final, okay? And because of that, what I'll provide is a practice exam for hopefully chapters 1 through 8. But in general, I think that we're going to be looking towards a final for a couple of reasons. One, well, we're still working on trying to find the best way to kind of proctor the exam, right? So we're not. I think I know, but we're not sure, and I'm not quite ready to provide an exam that is proctored or proctorable. So what we're going to have is a practice exam that you can take as a real exam to kind of test yourself and see where you're at, and that'll be probably over chapters 1 through 8, but maybe it'll be chapters 1 through 8.5, depending on when I finish it. And then if we can push through and get to chapter 10, that would be nice, but we might not. Then the final will probably be over 1 through 9 or maybe 1 through 10. Okay, sorry we took extra time. Anybody have any questions? You can hang around. Otherwise, I will see you guys, talk to you on Friday. True? Today's Wednesday?
I have one question.
Yeah.
So with like the ionic, I just wondered. So I know that to stabilize, we took away 1 electron from the 6p, but why did we also have to take away from the 6s? Like, could we have just taken away that 1 electron to make it stable, or was it necessary to also do the 6s?
Well, you just, in general, the idea is from this type of approach, what we are doing is we're predicting likelihood of stability. And so by removing 1 electron there and making that 6p empty, it wouldn't be surprising to us then that a thallium plus 1 ion might exist, right?
Okay.
That's basically all we're doing when we do that.
Okay.
Okay. Any other questions?
I have a question.
Yeah.
When you're stabilizing, how do you know not to like take away the electrons from the 6s last?
How would you know to take away 6p before 6s?
Yes.
All right. So the way that we know that is 6p and 6s actually do differ slightly in energy. All right. So 6 is our N value, our energy value, but 6p P and S can be used as a differentiator between energy when they have the same n value. So when there are two sets of electrons or two electrons that have the same n value, the L value can be used to distinguish energy if the n values are the same. Okay, so the L value does tell us a little bit about information in terms of energy, and so because 6p is higher than energy, that's how we knew we wanted to take the 6p's away first. I don't know if that answers your question. Does that make sense? Or who was that? Was that who was it that asked that question? Did they get kicked off?
I think it was Sarah.
Oh, Sarah, are you there? Sarah?
She's typing.
Oh. Okay. Good deal. You bet. Any other questions?
I have one quick question regarding the energy levels again. So would that mean that F is the highest energy? Out of the 6s and 6p, if we're talking about
6s, 6p, in terms of energy for thallium. So if we have thallium, we have xenon. Let me just bring it up again. So these electrons are our valence electrons. They're the ones that are going to be lost first. But in terms of, did you say energy in terms of comparing 5D to 5S, for example? Is that what you were saying?
I'm kind of figuring out like what determines the higher energy. Is it the n value or the letter corresponding with it?
It's the n value. That's why we call it the principal quantum number. So that's the principal in the first one. But when you have the same n value, then the L value is used to identify the higher energy.
Okay, that makes sense. And D would have more energy than 4F.
What? Say that again?
5D would have more energy than 4F.
That's right. Yes, good.
Okay, cool. Thanks. That's it.
All right. Any other questions?
I have a question. Did you, by chance, is all the papers and stuff posted? The slides, or the papers you handed out in class, the slides.
So let me bring this over here. On the home page there, this is the link to the chapter 8 slides.
Okay.
Can you see that okay? And chapter 9 are there as well.
All right, awesome.
Okay, good. Any other questions?
For the do you have the grading scale posted online somewhere? I couldn't find it. For class.
Let's see. It might have gotten sucked out of the syllabus because, wait a second. Do we not have that? Oh, is it on the home page here? Let me, let's see, do I have, let's see, I'm in the middle of, my computer is not behaving well for these online classes, and so they gave me a loaner. And so, oh wait, I do, no, let's see, that's not it. Oh, yep, I do have it. Okay, so let me,
link on the homepage.
What's that?
There was a link on the homepage.
I don't know if that's the syllabus we're talking about.
Does it take you to the syllabus though?
It takes me somewhere that shows some sort of grading, but I'm not sure if that's.
Oh, there we go. That link there. Yeah, that's it. There we go. And let's see if we got the grading on there. So I think that, yeah, the figure here You guys can't see any figure there, can you? I'm not sure if it's my browser or whatever. Do you see, who was that? That was you, Chance?
Yeah.
You don't see the grading scale there, do you?
I don't see a scale. All I see are the equation of total points with the exam.
Yeah. Whoops, that's not what I wanted to click. So the figure here, this is the grading scale right there. I can't get this to, let's see if I can copy that. I'll try to paste it in again, just directly like this. So when I paste it in, it doesn't show very well. Let's see if I can. That should be okay. Does that show up now? There we go. You see that there, Edgardo?
Yes.
Okay.
Then I've uploaded it, reloaded it, it's there now.
Okay, great.
And is the final cumulative as well, or just the
Yes.
final result?
Yep, the final will be cumulative. That's right.